So picking up where we left off, looking at conditional probability formula. If events A and B are not independent, because otherwise conditional probability wouldn't matter if they are independent, then the probability of A and B is equal to the probability of A times the probability of B given A has occurred. Yes, I have it. So the first example here, if you pull 2 cards out of a deck, what is the probability that both are spades? So we have the probability we're going to let event A be first card is spade, and event B be second card is spade. So we have a probability of A and B, just as the formula says here, probability of A times the probability of B given A has occurred. So what is the probability of getting a spade on the first card? Very good. Yeah, there's 13 spades and there's 52 cards. What's the probability of getting a spade on the second card given the first card was a spade? Well, how many spades are left? And how many cards are left? So now to calculate this, we just simply multiply both of them across. 12 times 13 is 156. 52 times 51, 2652. And I know I've said it before, but you don't have to reduce it. Any questions on that one? Okay. So if you draw 2 cards from a deck, what is the probability you will get the ace of diamonds and a black card? So our 2 events are probability of an ace of diamonds and probability of a black card, given we got the ace of diamonds. So what's the probability of getting this ace of diamonds? Well, how many ace of diamonds are there? 1. How many cards are there? Okay, now that I've pulled out and I've gotten the ace of diamonds, what's the probability of getting a black card? So how many black cards are there in the deck? And diamonds are red, so you have 2 suits, right? Clubs and spades. So 26. Now how many cards are left in the deck? 51, because we're taking 1 out. So our probability of an ace of diamonds and a black card is 1 over 52 times 26 over 51, or 26 over 26, 52. Is that what it was? Yeah. And again, yes, I know, it will reduce the 1 over 102. But again, why do it if you don't have to? It's too easy to make a mistake. Okay. Does everybody have that, or do I need to? Didn't look up before I scrolled down. Everybody get it? Got it? Scream if you need me to wait. Okay, so we have a home pregnancy test was given to women. And again, we're not getting into politics here. Then pregnancy was verified through blood tests. The following table shows the home pregnancy test results. We want to know the probability that you're not pregnant given the test was positive. So we're told the test was positive. So how many people got a positive test? 75, right? And how many of them were not pregnant? So our probability for that is simply 5/75. Now, how many people are not pregnant or have a positive test given that they are not pregnant? So how many people were not pregnant? And how many of them got a positive test? Very good. See the difference? Even though it really looks to be the same, it's different probabilities because it's based on what has already occurred. Any questions so far? Look at that pretty formula. What do you think? You want to tackle that one? I don't. I think this is beyond the scope of this course. I think it was a graduate level statistics course before I even looked at Bayes' theorem. So that brings us to our next topic, counting. Does everybody know how to count? So let's see how this works. Suppose at a particular restaurant you have 3 choices for an appetizer: soup, salad, or breadsticks, and 5 choices for a main course: hamburger, sandwich, quiche, fajita, or pizza. If you're allowed to choose exactly 1 item from each category for your meal, how many different meal options do you have? So let's do this the long way first. Soup, salad, breadstick. Now with my soup, I can have a hamburger. I can have a sandwich. I can have a quiche, although I don't know why anybody would want one. A fajita or a pizza, right? But also with my salad, I can have a hamburger, a sandwich, a quiche, a fajita, or a pizza. Also, if I choose breadsticks, I can have a hamburger, a sandwich, a quiche, fajita, or a pizza. So how many possible meals are there? 15. Which just so happens to equal 3 times 5. So you tell me, would you rather do it this way or this way? I know my choice. But I like math. Some of you might like drawing, and I'm going to draw it out. Everybody got it? So that brings us to the basic counting rule. If we are asked to choose 1 item from each of 2 separate categories, where there are M items in the first category and N items in the second category, then the total number of available choices is M times N. Sometimes this is some kind sometimes called the multiplication rule of probability. What gets me is, why do they use M and N? They both sound the same. Make it A and B or X and Y. So let's see what we got going on here. There are 21 novels and 18 volumes of poetry on a reading list for a college English course. How many different ways can a student select one novel and one volume of poetry to read during the quarter? So we have two lists. We need to choose one from each. So we'll use our basic counting rule, which says take 21 and multiply it by 18. So 21 times 18, 378. And of course, if you like to draw, you can draw out all 378 possibilities. Any questions on that? Okay. So now we're back to our restaurant again. We have 3 choices for an appetizer. We have 5 choices for a main course. And we have 2 choices for a dessert. How many meals do we have? That's the easy one. Any questions on that? So essentially, it can be extended to more than two lists. You could have 10 lists. You get some pretty large numbers, but it could be. So a quiz consists of 3 true or false questions. And how many ways can a student answer the quiz? So we have 3 questions, which have 2 answers each. So how many different ways can you answer the first question? 2. How many different ways can you answer the second question? 2. How many different ways can you answer the third question? 2. Multiply and 8. This seems awfully easy, don't it? I always heard probability was hard. See what we can do about that. Now we're going to start talking about permutations. Order matters. So how many different ways can the letters of the word math be arranged to form a 4-letter code word? So we can start out with just math. And we can go HT. And we can go MTAH, MTHA, MHAT, and MHTA. Okay. Then we can start with A. AMHT, ATMH, ATHM, AHTM, AHMT. Anybody see the pattern here yet? EHAM, PMAH, PMHA. What's letters left? H, ATM, HAMT, HMAT, HMTA, HTMA, and last one. Thank goodness. So how many do we have? How many?
16.
How many down? 6. How many across? How many do I have? What's 4 times 6? 24. Is that right? Everybody see that? Anybody familiar with factorial? Anybody? Couple? So factorial is symbolized by putting an exclamation mark after usually the number. So in general, n factorial is equal to n times n minus 1 times n minus 2 all the way down to 3, 2, 1. To put this 7 factorial equals, actually, let's use 4 factorial is equal to 4 times 3 times 2 times 1, which is 24. So had I known about factorials before, I could have just said 4 factorial and gotten the answer to this. So arranging n things in at a time where order matters, the number of possible permutations is n factorial. So we have here, how many ways can 5 different door prizes be distributed among 5 people? So I would say 5 factorial, which is 5 times 4 times 3 times 2 times 1, or 120. But in case we hadn't figured that out yet, I have 5 prizes, I have 5 people. How many people can I give the first prize to? 5, right? How many choices for the second prize? Now that I've given somebody 1, they can't have another. So now there's 4 people left, right? And then 3, and then 2, and then 1. So as you can see, it's the same thing. If you don't recall that it's 5 factorial, you can work it out the same way. Any questions on factorial? Because we will be using this quite a bit from here on down. So we have a charity benefit is attended by 25 people and 3 gift certificates. I don't know why I'm having trouble saying certificates today. Are given away as door prizes. 1 gift certificate is in the amount of 100, the second is worth 25, and the third is worth 10. Assuming that no person receives more than 1 prize, how many different ways can the 3 gift certificates be awarded? So order matters because they're different values. So I have 25 people, and I'm going to give away the first gift certificate. How many possible people can get it? 25. Now, since that lucky person got the $100 gift certificate, they can't get the next one. So how many people can get the second one? And then how many can get the third one? 23. So we have 25 times 24 times 23, which is a whole lot. 13,800. That makes sense? Okay, now we have 8 sprinters that made it to the Olympic finals in the 100-meter race. And how many different ways can the gold, silver, and bronze medal be awarded? We're giving away different prizes, so order matters. So how many ways can I give away the gold? 8. Now that you got the gold, you can't have the silver. So how many ways can I give away the silver? And then the gold, bronze. And what do we end up with here? 336. Yes, thank you. So what does this bring us to? Again, we're talking permutations. And for some reason that got typed wrong. So we say that there are, for lack of a better way to put it, NPR permutations of size R that may be selected from among n choices without replacement, and when order matters. That's the big one, when order matters. And here is our formula. Taking n, the number of permutations from n items taken R at a time equal to n factorial over n minus R factorial. So I have 9 paintings and have room to display only 4 of them at a time on my wall. How many different ways could I do this? First thing to think. I don't have to worry about replacement. There's no way replacement we have to even consider. Does the order that I hang them matter? Yeah. Sure it does. If I put painting A here and B here and C there, is that not different than C, B, A, D? Isn't that a different display? So order matters. That means we're going to use permutations. And N is, we have 9 paintings, and we're displaying 4 at a time. So 9 items, the number of permutations for 9 items taken 4 at a time. That's what we're looking for. This will be on your exam, by the way. So according to the formula, we have 9 factorial over 9 minus 4 factorial. And we have 9 factorial over 5 factorial. Now there's 3 ways to look at this. We can do it the long way. Right, and just multiply it out. 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2.
15,120.
And this is okay for this because the numbers aren't quite so large. And it's easy enough to do. Then divide that by 120. And I get 3,024. That's one way to do it. And like I said, with 9, it's not that big, but as it gets larger, it gets exponentially larger. And eventually, most calculators, I want to say about 20. Once you get to 20 factorial, it may even be less than that. You get an error code. But there's a shortcut. So 9 factorial over 5 factorial. So again, we can write this all out. And then we can do that one thing I've told you you don't have to do. We can factor out or divide out the common factors. Right? So now I just have 9 times 8 times 7 times 6, which I hope equals 3,024. Now, back in the dark ages, when I learned to do this, we weren't allowed to use calculators. So we learned another trick. 9 factorial over 5 factorial. Well, this is simply 9 times 8 times 7 times 6 times 5 factorial, right? All right, because I have 5, 4, 3, 2, 1. These cancel out, and now I just have this, which again, I hope comes to 3,024. And which method you use doesn't matter to me, whichever you're most comfortable with. I will say doing it this way with larger numbers, it's not going to work. Your calculator will give you an error message because it don't have enough digits on the screen. And it'll go up quick. Essentially, once you get to 10, you're going to be adding another digit on the end each number higher you get. What is it, 8 digits these calculators hold? So that's 6. So at 10, it'd be 7. At 11, it'd be 8. And beyond 11, you're going to get that error message. So work on reducing it. Would be my recommendation, but again, whichever way you're comfortable with. Excuse me. So, how many ways can a 4-person executive committee, president, vice president, secretary, treasurer, be selected from a 16-member board of directors of a nonprofit organization? So, first question, does order matter? Yes, because we're choosing a president, vice president, and so forth. So we can use our permutations. We have a 16-member board, and we're choosing 4 of them. So we set up our equation as 16p4, which is 16 factorial over 16 minus 4 factorial. And like I said, I don't think you can calculate 16 factorial on your calculator. Another thing is somewhere in some of these, I know this one has it, I'm not sure how to get to it. There is actually a way to calculate factorials on these just by pushing a number and going through some series of things. I'm not sure exactly what it is. I haven't looked at the instruction manual in quite a while. But this is just 16 factorial over 12 factorial, right? Which is 16 times 15 times 14 times 13 times 12 factorial over 12 factorial. This and this goes away, so I'm left with 16 times 15 times 14 times 13. Sixteen times 15 times 14 times 13. That is 43,680. Any questions on any of this? And as I said, the test will have the formulas on it. So that's all I need to record today.